minutes. All right, this will all be recorded. So this is from the EKS course. So basically, containerization, the best practices for building applications is they want you to have it be portable, scalable, continuously deployable, basically cloud deployable, obviously, and they want you to be declarative, like this is the end state that we're looking for. So when it comes to container fundamentals, though, what would happen is that before containerization came along, which is why this is so popular, this is why Docker and subsequently Kubernetes are so popular, is because this is what it looked like before we started standardizing our application packaging. If you deployed a Java app, it might be in an ER file, WAR file, or jar file, probably a jar file. And then, Ruby might be using like Capistrano, like frameworks are all over the place for deployment. This is the problem. So then what happened is that Docker came along and said, you know what if we just like, what if we just standardize containers the way shipping containers are standardized? What if we said, let's just make it so that everything is the same. So that way, as long as I have the infrastructure to deal with a container, the application inside is just going to work. Whether it's deployed using, jar files, WAR files, Python, Iron Python, C Python, Iron Ruby, whatever it is. What if we just standardize the packaging so that you could just deploy it? You could just run it. And everything you need to run that process, that application, is just inside the container. So again, if you want to run this, you just need to have the ability to manipulate a shipping container, or in this case, a container, a software container. Because previously what we were doing is we were putting these apps in their libraries on top of an operating system, and that could get pretty kludgy because you probably only get one app on that operating system. It just depends. And then we started doing virtual machines, which makes a lot of sense, except we started copying the guest operating system. Why were we copying the guest operating system? Well, that's because that's all we knew. And then here we are in containers. And the only thing I take issue with is don't look at those libraries that are going across containers. First of all, no one's going to do that. I don't even know why that's there in the picture. But what this is supposed to show is that each of these application containers is independent and contains everything it needs to run. And by the way, it's not sharing libraries with other services, right? And so what's happening is that those containers, as long as you have the containerization platform, they're going to run. Doesn't matter whether it's Java, Go, blah, blah, blah. Nothing needs to be on the operating system other than the kernel for that container to function. So what happens is that when you put an application in a standard packaging format, in this case, containerization, like a Docker container is nothing more than a format of containerization. And once you do that, then you get portability, you get scalability horizontally, right? And then you can do things like continuously deployment. And then what happens is that this becomes ideal, right, for things like microservices. So then you can start splitting things up into tinier applications, package them up, and let different teams work on different technologies. And the infrastructure team can just respond to containers. They don't respond to what's inside the container. Now, here are the components of a container. First, you've got a container image. Now, this is a set of instructions. Sorry, the container image is a product of a set of instructions that come from a file called a Docker file. That Docker file has things like copy this file into the container, put Java into this container, call Maven and have Maven build something, call Gradle and have Gradle do something, right? These instructions all then add files to this container image, and that container image is now deployable as a running container. How many copies of this can we have? How much space do you have? And so what it's going to do is that container image is now immutable, and they add a thin read-write layer on top of it, allowing, people to manipulate the container, but only temporarily, because unless you put a volume on this, that thin read-write layer is going to go away as soon as the container is shut down. So you have to add a volume to it. Think of that thin read-write layer as like instant storage. It gets deleted the minute the system shuts down, right? Same thing. If you want to make that permanent, you have to attach a volume to it, right? And so that Docker file built a container image with a set of instructions. Each change to that container file system became a layer that makes up that container sandwich, if you will. So on the right, we have running containers. On the left, we have the base image that started those running containers. Now, composing a Docker file involves, first of all, citing your source. So in this case, we're going to pull from CentOS. Then we're going to run a command. In this case, we're going to update and then install Apache Web Server. We're going to expose port 80. We're going to copy our run script into the container. We're going to change the permissions on that run script. And then we're going to run that run script to get Apache up and running. Notice that each of those instructions added a layer on the right-hand side. This is how you build a container image that then gets used as a running container. Now, in this particular case, if we start with an image, we're going to choose node 10. And why not Ubuntu latest? Because we try not to use the latest tag. That latest tag is a moving target, and we try not to do that in our builds because we don't want just the latest software always creeping into our builds. So we're going to use an explicit number. And then we're going to say, hey, I want to set a working directory. So everything that gets copied is now run from this working directory. I'm sorry, everything that's run is now run from this working directory inside the container image. So we set up a working directory and we called it user source app. Then we copied in our dependencies, and what we did is we copied in package.star.json and we put it in our working directory. And then we installed the application by basically running npm install. We basically copied in our server.js. And then we set a networking port. In this case, we used expose because that's the proper command to expose a hole in the container that's going to listen. It's going to hit port 80 on the particular JavaScript thing that we're using, right? And then we're going to start the application, which is going to be the command. We're going to run node server.js. So when someone runs this container, what's going to happen is that everything's already in the container, but on port 8080, it's going to have a hole in it. It's going to run node server.js, right? This is how we get a running container is we create a declarative file like this. Sorry, this is not declarative. I apologize. This is basically a procedural file that says from here, do this, 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 and this. And this is how you create what's called process virtualization, right, which is also known as containerization. You're running a single process inside of this container. And if your operating system has the containerization software, you can now run this. So that's the fundamentals of containers. Let me scroll past this here. So by the way, this is, our business driver is that Docker is, and really Kubernetes and containerization, well over the vast majority of the private sector in particular, the workloads are on containerization. So they're in containers. So this is the standard de facto way that most people are deploying their applications now. The vast majority are doing containerization. There's still a lot of virtual machines out there because you need virtual machines to run containers. But for the most part, application deployment has now added this extra layer of containerization. So we're kind of like skipping past this for a second, and I'm going to come back to microservices. I want to skip over to containers just to continue that story, right? So this is what it looked like before. This is us standardizing on containerization. And then, as mentioned, everything that application needs to run, including JVMs, Python interpreters, everything needs to be in the container because it's not going to get installed on the operating system. The container is going to bring everything it needs to run the application. These containers are tiny, by the way. If we, for example, go to the most famous container registry in the world, hub.docker.com. Oh, that's weird. Hold on. Didn't like that. Huh. Anyway, what's going to happen, for example, is let's say we go search for Redis. These images, by the way, are really tiny. So if we look at these, this is 40 megs in size. If we peel this back, it's basically adding in a bunch of files. Looks like it's running bash, adding a group, setting up some environment variables, making a directory, setting up a data volume, right? And then it's going to run, it's going to run Docker entry point unless you specify something else, like Redis server, which is what it's going to do by default. So just know that like these are super fast, super lightweight process virtualization. So you can run Postgres, you can run anything that will run on Linux non-interactively. You can run it inside of a container. So that pretty much is everything. Notice that there's a bunch of containers for AWS out here, including ingress controllers, the CLI tool. So if you want to run the CLI tool inside of a container, instead of installing it on your local system, you could do that as well. So containerization is nothing more than just process isolation. You're just putting it all into a box, a container that can now be run. Now, these levels of abstraction, as you saw before, it makes containers smaller, lighter, and faster than virtual machines. Plus, they don't have the attack surface. Now, isolation can be a little bit of a challenge because while they are highly isolated from each other, we've been doing virtual machines for 20 years. We've been doing containers for 7. So, there might be a few more holes there, maybe. So in this particular case, notice the containers are running on top of the Docker engine because they're all encapsulated in their own little containerization like packaging. So you can run containers if you want natively on EC2, but just note that AWS actually does have container services that they want you to use. So they have what's called Elastic Container Service and the Elastic Kubernetes Service. And this is how you run containers on AWS. Now, there's a funny blog post called 17 Ways to Run Containers on AWS, part 1. And there's a part 2, like, how to run 17 ways to run containers on AWS. A lot of them are silly. You would never run containers that way, but you could, right? But mainly the 2 container services are ECS and EKS, which we'll talk about in a second. Now, if I go all the way back to microservices, which the reason that microservices and containers are talked about so much is that microservices are perfect for things like loose coupling. Sorry, containers are perfect for things like loose coupling. And microservices really loves loose coupling, independence of scalability, independence of deployment, independence of interconnection, independence of databases. Microservices really love that kind of loose coupling. It's a big deal for the microservice architecture pattern. And so with microservices, what we're doing here is that you're actually taking a monolithic application that has all of the business concerns, and you're separating it out into 3 microservices. In this case, a user, a topic, and a message service. So then you can use that service, those independent services can all talk to each other through APIs, and they can now all scale independent of one another. Now, when you architect for microservices on AWS, you're typically going to use something like an Elastic Load Balancer or an API gateway to kind of like divvy up the different endpoints and let them go to different systems or different containers. So you see users, topics, and messages now corresponds to the three services we just saw on the previous slide. And those could go to a bunch of containerized applications that are sitting on ECS or EKS. And by the way, that could be Lambda, they could be EC2, they could be an ECS cluster. I don't think that an application load balancer, well, I mean, I know it can target an IP address, so I don't think it natively integrates in with EKS, but I know it does with ECS. And so the other thing to think about is that Amazon does have this X-ray service that I mentioned before that allows you to get end-to-end visibility into all of your microservices and the calls that a customer makes when it goes on its journey. So if a customer comes into your front end, hits your back end, hits DynamoDB, hits API gateway, et cetera, X-ray will allow you to see all that, so you can actually see how it flows through your AWS ecosystem. So you can get a service map, which is actually pretty gorgeous to look at, and you can drill in and analyze issues. It'll also give you all the latency choke points. Where is it slowing down, right? Where is it not working as fast as it could? It is based on open tracing, so it uses traces along with segments and subsegments to control like where you dive into the application workflow. So notice that here it's going to Lambda and then hitting, a bunch of services, and then it's using a service map. That service map will show you all of the AWS services that user is traversing to run that code. So bottom line is just know that containers go along really well with microservices, and that Amazon has a observability tool called X-ray, which will let you dive into all of your calls for a particular user, including AWS services. All right, let's pop back over to container services. So I mentioned that ECS and EKS exist right inside of AWS. Both of them, by the way, need what's called a registry in order to function, which means whether you're running an ECS cluster or an EKS cluster, they have to download a container image. The container image was that thing that we built before with a Docker file. Those images have to live in a repository that ECS and EKS can pull from. And so Amazon has its own like container registry service called ECR. And it basically allows you to push images up there and then download them as you need to. Now, ECS will use the ECR to pull those images down. And one thing I just want to emphasize here is that notice that you can launch them on EC2, or you can launch them on serverless, also known as Fargate. But note that it's pulling the images from ECR into whatever it's using. So it's either pulling them into EC2 images, or it's pulling them into Fargate profiles. So here we've got an application load balancer up front. And if I hit API users, it's actually going to the, in this case, it looks like it's going to the user's load balancer, which then, by the way, is going to refer back to these EC2 instances on a particular port. Now, what this is that this is a service, by the way. This service acts as a load balancer. It's not actually a real load balancer. And so what this does is if traffic comes into API topics, it actually hits this service, and the service directs to the location of the various tasks. So you can think of a service as kind of like a load balancer. At least that's the way it functions inside Kubernetes. Note that you can run 2 containers, you could run 50 containers as long as you have the capacity to do it. Now, in this case, the ECS cluster is actually, this cluster is actually using EC2 instances. So this is not a Fargate profile. Fargate only runs the actual containers. It doesn't actually show you the systems that are running. So this is an EC2 launch type. Now, if this was Kubernetes, the real difference between Kubernetes, between EKS and ECS, is that ECS is Amazon's proprietary container system. EKS is a CNCF certified distribution of Kubernetes, which is an open source product. So ECS is proprietary, EKS is industry standard. I got to tell you, ECS is easier to use, but EKS is more industry aligned and has far more capabilities than ECS does. So you got to pick which one you want to use. In general, if you can stand the learning curve, I would say go after EKS. But if you're just standing a few things up, just use ECS. Use the Elastic Container Service. Don't use the Elastic Kubernetes Service. This, by the way, works the exact same way. I want you to note, once again, we've got an EC2 launch type, and we've got a serverless Fargate launch type. Works the same way as it does over on the ECS side. Now, when you create a Kubernetes cluster, you are creating what's called a data plane, which is comprised of worker nodes, and you can create a control plane, which has master nodes. When you use EKS, Amazon hides the control plane servers from you because you can't touch them or mess with them, but you can still start and manage your worker nodes. Worker nodes, by the way, are where all the data runs. Now, I warned you that if you saw Fargate by itself, it means serverless. That's all it is. So either with EKS or ECS, they have a serverless launch type, which means you launch your pod and it gets put onto a virtual machine that is the exact same size of the pod plus 256 megs of memory. So it's kind of interesting that Amazon came up with this, but they use these micro VMs called Firecracker VMs, and they spin them up really fast, and they put containers, and they're just slightly bigger than the container itself. So note that you have options to either use EC2 or serverless for both of the managed services for containers. Okay. Note also that we've looked at this before, where we've seen Lambda, then Fargate, then ECS, EKS, which is EC2 launch types, and then we've got EC2. As you go up the chain, Lambda is the easiest to use, least amount of control. EC2 is the hardest to use, most amount of control. So don't forget, ECS and EKS both have EC2 and serverless launch types. The serverless is called Fargate. And remember, you're going to use an Elastic Container Registry and ECR in order to be able to use these two services. Questions of any type about containerization?
Sir, if I was to use EKS, do I have to use ECR?
You can actually pull from a public registry if you want to. Most people don't do that. Most people will run their own private repos on Amazon. So you don't have to use ECR unless you really want to. So, knowledge check. Which of the following are characteristics of microservices? So loosely coupled and independent, right? That's what we're looking for. Independent. Certainly not tightly integrated, certainly not redundant, right? Okay, which of the following are characteristics of containers? Good, A and D. Portable, scalable, and repeatable, right? They certainly don't require a hypervisor. They do require an operating system, though. And they're not automatic. Wish they were. Okay. Containers in Amazon ECS are logically organized into a good. So both EKS and ECS do require you to create a cluster before you can deploy worker nodes. So just know that's part of the process. All right, I mentioned this in passing. What are two of the following are components of a Kubernetes architecture? Excellent. Good. Data plane and control plane. Perfect. Okay. Why would you select to deploy your containers to AWS Fargate a la serverless over Amazon EC2? Good. To avoid manual infrastructure updates. That sounds correct. Questions of any type about either containerization, microservices, just in broad strokes, or containers in general? Okay. We're not at a phase, by the way, where we get to choose our own adventure. Okay. So we're going to choose our own adventure here. All right. So we can, first of all, we're going to take a short break. So we're going to take 15 minutes here in just a second. My question for you, though, is I want you to think about this, and we're going to talk about it when we get back, right? Is that I can start the exam prep early because we're actually a little ahead. We're about 30 or 40 minutes ahead of where we normally are. So normally, by the way, we could be done for the day and just pick it up tomorrow. So when you get back, I want you to think about whether you want to go a little bit further so we can have a shorter day tomorrow. B, do a longer exam prep, and so we can do that until about 4:45 or 5, whichever works, best for you all. I can stay till 5. That's not an issue at all. Or we could just do a shortened, like a 30-minute exam prep and just be done a little early today. So your options are be done early today, be done early tomorrow, or do a longer exam prep until 5 o'clock today. So think about those options or what you might want to propose. But we got a little bit of a choose your own adventure going on. So we've got options that we can do. Okay. So think about that. We're going to take a 15-minute break. So it's 3:50 now. So take 15 minutes and come back. Well, let's make it 5 after 4. Okay. So 5 after 4. So be back in about 14 minutes.